This video is the third video on Chapter 40, Separable Differential Equations. And the last thing that I'm going to do for Chapter 40 is to work through example 246. And so this is an example that looks very complicated and very intimidating at first. We're being asked to find the amount of salt in the tank at time t as a function, and we're given not so much about the function itself, but we are given a lot about the rate of change of the function. And so we start initially, we have 100 gallons, we have a 100-gallon tank. We have a 100-gallon tank, and the brine that's in the tank contains half a pound of salt per gallon. So initially we have 50 pounds of salt in the tank. That's what this initial condition is. So we're going to let Q, which is actually a function of time, be the amount of salt in the tank at time t. We want to find Q. This is our goal. We're not given a lot of information about Q directly, but we are given a lot of information about the rate of change of Q. So that gives us this equation. Let me explain this equation. So dq dt, this is the rate of change of salt with respect to time. We have water, we have brine that's flowing in, we have brine that's flowing out. So this gives us our rate of change of the amount of salt. The salt that's coming into the tank is 1/4 of a pound per gallon. So we have 1/4 of a pound of salt per gallon that's coming into the tank at a rate of 4 gallons per minute. So that's where this comes from. This is our intake. So this is the rate that salt is coming into the tank. But salt is also leaving the tank. Salt is leaving the tank at this rate. Where does this come from? Well, remember, the solution is being kept thoroughly mixed. So we have the amount of salt in the tank divided by 100. This is the amount of salt per gallon because we have a 100-gallon tank. So the salt divided by 100 it's our concentration. It's the amount of salt per gallon, and our brine is flowing out at a rate of 4 gallons per minute. So it's coming in at a rate of 4 gallons per minute, leaving at a rate of 4 gallons per minute. So this is the rate of change of the amount of salt at time t. It's coming in at a certain rate, it's leaving at a certain rate. So this is the rate of change. Keep something else in mind. We started with half a gallon of salt per gallon, and the solution that's coming in is 1/4 of a pound of salt per gallon. So it's being diluted. Okay, so the amount of salt in the tank will never be less than 25 because that is the concentration. 1/4 of a gallon of 1/4 of a pound of salt per gallon is coming in. So we'll never have less than 25 pounds of salt in the tank, and we'll never have more than 50 pounds. So the amount will always be between 25 and 50. So we have this differential equation that we've set up with our initial condition Q of 0 is equal to 50. We'll simplify the differential equation here. So we simplify 1/4 times 4 is 1, and then we have Q divided by 25. We want to be able to integrate, and so we'll do some algebra here, get a common denominator. So we have dq dt is 25 minus q divided by 25. Now it looks like a differential equation that we've been working with in the previous example. Okay, so it's a separable differential equation, so now we separate it. We put the q terms on the left and the t terms on the right. So now we have a separable differential equation. Now we apply the integral operator. So we integrate on the left, we integrate on the right. So we have the antiderivative of 1 divided by 25 minus q. That's -1 times natural log of absolute value of 25 minus q. And then we have an antiderivative of a constant. We just have our constant times t plus a constant. Now, to find our constant, we go back to the initial condition. Q of 0 is equal to 50. That means at time 0, when we started, there was 50 pounds of salt in the tank. So we substitute T of 0. On the right side, we just have C, and Q is 50. So we have 25 minus 50 is negative 25. Take the absolute value. So we have natural log of 25 times negative 1. So that is C. C is negative natural log of 25. We come back to our equation up here, substituting negative 1 times natural log of 25 for C. Multiplied through by negative 1 to make this look a little bit prettier and more manageable. And so now we have natural log of something is equal to natural log of something else minus this term. So we have we apply the exponential function to both sides. So we have e to this term is simply absolute value of 25 minus q. E to this side, so we have e to the natural log of 25 minus 1/25 t. Use our properties of exponents here. Remember what we said. Q is never going to be less than 25. Q is between 50 and 25. So the absolute value of 25 minus Q is Q minus 25. Because we know that Q is between 25 and 50. Properties of exponents here. And now we just have e to the natural log of 25 is 25 multiplied by e to the negative 1/25 t, and then we've added 25 to both sides. So this is our equation. Let's do a couple of things. When we substitute 0 in for t, what do we have? We have 25 plus 25, which is what we should have. Let's notice something else though. It's not part of the problem, but just to notice this. If we take the limit as t tends to infinity, what happens here, this term goes to, so as t goes to infinity, we have 25 divided by something that's getting very large, this goes to 0. So as t tends to infinity, this term goes to 0, so q goes to 25, which is intuitively what we think should happen because our brine that we're pumping in is it's 1/4 of a pound of salt per gallon. So as we do this more and more, we're going to dilute this, and the limit as t goes to infinity is going to be 25 because we have 1/4 of a pound of salt per gallon times 100 gallons. So as t tends to infinity, this term goes to 0, so we have 0 plus 25, which is 25.